Okay, so picking up 4-3 notes here with example 1. Particle is moving along the x-axis as shown here. It experiences a force. So this kind of takes up right where we left off with the force versus displacement graph. And I know you guys are thinking hopefully that this example is too easy, right? So the particle does have 2 joules of kinetic energy as it passes 0. So that's important because they're giving me basically a starting point, right? They're telling me how much energy it has to begin with. But other than that, it really hopefully is very easy. They ask me how much kinetic energy does it have when it reaches 4 meters. So I know it starts with 2 joules of energy here. If I want to find out how much kinetic energy it has at this location, I want to figure out how much energy it has gained, and the energy is just really the work done on it, right? So the area underneath this curve represents the work done on the system. Because it is positive, because it's above the x-axis, it's going to be positive work, and therefore it's going to equal a positive change in kinetic energy. So whatever this number is, I'm just going to then add that to the kinetic energy that I started. So finding the area, pretty easy, 1/2 base times height. So 1/2 4 times 2, which is 4, right? So the work done here is 4 joules of work, which tells me again my energy increased by 4. So my kinetic energy at 4 meters is 2 plus 4, or 6 joules of kinetic energy. Right, so like I said, hopefully a very easy example to get through here. It does illustrate once again the importance that the work function, the energy function, is just the integral. It's the area underneath the force function. So not too. So a quick side note before we get into kind of more of the maybe graphical and other representations. What if we know it's a constant force? Then how do we find work? So then, just like the very first slide when we started these notes, we know that if it's a constant force, work equals the force times the displacement, but it is once again very important that they're the same direction. And so that's why the equation actually then throws in the cosine of theta, right? Cosine of theta suggesting that if I had a force that was off at an angle, so if I was exerting a force that was pulling upward at an angle, but the box or whatever was actually moving just off to the right, then I would take the cosine of the angle so that I figure out the two components that are going the same direction, and that would be my work, right? So the big part about this, the reason I threw this slide back in here, we can only use this equation if you know that it is a constant force. If the force varies, or if it's varying at all, or if it's a quadratic function or something that's not constant, then I cannot use this expression. So you do have to be very comfortable on when you can and cannot do this, but I think hopefully that's pretty straightforward. Okay, so example 2, hopefully a pretty clear example of the point we just illustrated, right? So a rope is inclined at a 45-degree angle, pulls on a suitcase through the airport. The tension in the rope is 20 newtons. How much work does the tension do if the suitcase is pulled 100 meters across the level floor? Okay, so my suitcase is just a box because I'm not very exciting. And then I'm pulling with a tension at 45-degree angle, and the tension here is 20 newtons, right? So it is saying that it's pulled 100 meters across the floor, so it does try and make it clear that we're going 100 meters horizontally, not at the angle. So once again, this is just a very important one for illustrating the idea that if the force is offward at an angle, if it's at an angle, then I cannot just use the full force, right? I don't just do work equals 20 times 100. Instead, what do I have to do? Well, you can do one of two things. One, if you trust the equation and you know that the cosine works when it's the angle between them, you could do that. But more importantly, I want you to kind of realize where it comes from, right? If I want to figure out the work done, I want the force in that direction, which is just a cosine component, right? It'd be the force times cosine, and then times the distance in that direction. Right? So that's where the equation is coming from. So it's just 20 times cosine of 45, and then times the distance of 100. So of course you guys all know the cosine of 45, right, is just radical 2 over 2. So this ends up being what? Just radical 2 times 1,000. So the work, I believe, is then about 1,414, right? So radical 2 times 1,000, 1,414 joules. Obviously the decimal continues on, but I'll round it off there. So again, hopefully a pretty easy example for illustrating we can use this because it is a constant force. And I just need to make sure I am accounting for the angle if it's at an angle, right? So watch out for the little details like that, but nothing I'd expect you guys to. I threw this example in here because this was an example, we saw one similar to this on the homework last year, and it's one that was very often missed because we oversimplified it a little bit too much. So you've got the rocket that weighs 150,000 kilograms. You've got the thrust generated by the rocket of 4 million newtons upward. What is the rocket speed at a height of 5 meters? Well, the biggest thing is if we're looking at the force here, if we're looking at the forces, when it gives us the thrust, that's not giving us the net force. And that was often the most common mistake that I saw was we've got our rocket, it has a thrust upward of 4 million newtons, but that's not the net force, that's not the end result. That's just the upward force of the engines as it's accelerating upward, right? What does it still have working against it? Well, it still has the force of gravity then pulling down, right? So if I'm going to do work, if I'm going to use the relationship of work equals force times distance, which I actually will do here in just a moment, I just need to make sure that I'm finding the net force acting on that object. Otherwise, it doesn't really help me out. Otherwise, I'd have to find multiple works done by the thrust and the work done by gravity and find the difference between the two. But instead, I'm just going to find the net force and then take that times the distance. So finding the net force, once you've identified that this is not the net force, hopefully it is pretty easy. It's just then 4 million, right, minus the force of gravity. So minus my 150,000 times 9.8, right? So once I calculate that, my net force ends up being about 2,530,000. So that's the net force. And then I know the net force is going upward, right? So the net force is going upward, the displacement is upward. So my work done would be in the positive direction. So I've got my net force here of 2,530,000, and then I've got the displacement of 500 meters. So this is going to tell me the net amount of work done on it. So I end up with about 1,265,000 joules of energy. Right, so that's how much energy I end up gaining. The only thing you then have to be careful about that is, does all of that work, does all of that energy convert to kinetic energy? Well, no, it doesn't, right? Because we're also gaining height. So this is the total amount of work done on the rocket. But we have to realize that some of that work goes to the potential energy of gravity, and some of that work goes to the kinetic energy we end up with, right? So if I want to find the rocket's speed, I'm just going to find its kinetic energy and its velocity from there, right? So I know the work done, and then I can calculate the potential energy it's gained. So again, 1,265,000,000 joules of energy went into the rocket. Some of that was just lost in raising its height, right? Some of that was lost as it climbed to a higher altitude. So potential energy of gravity would be 9.8 times the height, so times 150,000, and then times 500, and then plus my kinetic energy, which would be 1/2, right? My mass of 150,000 times the velocity squared. So obviously, once I set this all the way up, hopefully it's not too bad, and then just solve for the velocity. So solving for the velocity, I get about 84.1 meters per second. For what it's worth, you absolutely could have just done kinematics, which probably for a problem like this would be easier. I just want you to see that you could do work as well. So with kinematics, right, once I find the net force, I could then just do force equals mass times acceleration, and then take the fact that it starts at rest, has an acceleration, and goes that distance, and I could find out how fast it's going. So again, they're really equivalent. You should get pretty much the exact same answer because energy is essentially the same relationship as kinematics. You're just throwing in the masses as well. But anyway, do whichever one you're most comfortable with, but I did want to show you how we could take a work and energy perspective on this question. So another quick concept check here, and this one kind of goes back to what we started the section with, but crane lowers a steel girder in place. The girder moves with a constant speed, which will be very important here as we move forward. Consider the work done, WG here being the work done by gravity, and then WT being the work done by the tension in the cable. Which of the following statements is correct? So if the crane is lowering the steel girder in place, so it's starting up here, and then the crane is obviously got a tension up there, but it's lowering it, which of those works would be positive, which one would be negative? Well, obviously, if the crane is lowering it, the tension's still pulling upward, and the force of gravity is still going downward, as always, right? But we're allowing it to drop downward, so the force of gravity is pulling it in the same direction, so that work would be positive. Tension is pulling it in the opposite direction, so that work would be negative. So my correct option here is option B. Work done by gravity is positive, work done by tension is negative. One other thing I want to throw in here, not necessarily related to this problem at all, but how much work is done in something that's moving in uniform circular motion? So if I've got an object, if I was spinning an object around in a uniform circle or a relatively uniform circle, if that object was attached to like a string or something and there was tension in the string, how much work is being done by the tension in the string? So think about that for a second. Hopefully you guys remember this, although it has been a little while. But anytime we've got uniform circular motion, the work done by the tension or the force of gravity or whatever's pulling it in the circular motion, the work done is always zero. And it is not because it completes a full circle. Right? Now you could make the argument that then it has zero displacement, so obviously it's zero there too. But it doesn't need to be a full circle. Even if it just goes around part of the circle, so even if it just goes this far, the work done by the tension would still be zero because the force is always perpendicular to the direction. Right? So at the top part up here, the direction of the object would be tangent to the circle. The force would be perpendicular, right? It'd be along the radius, and so the work done is always zero. So like I said, a bit of a side note, I know I kind of just threw that in at random, but that is actually a very important concept we'll see moving forward, particularly once we get back to circular motion stuff. So it is a good thing to think about it here since we're talking about work and energy anyway. But hopefully a concept that you guys kind of remember as it is. Anyway, moving on. So the last thing we have to talk about in this chapter, like I said, I mentioned in the very first part of the videos here, we're going to go back and we're actually going to revisit dot products and vectors. Now this is something you probably were taught in pre-calc, although you guys did have Davis, so who knows if you really learned anything in there, but hopefully you've seen this already, but it's worth reviewing even if you have seen it. So multiple ways we're going to work with vectors in this. We actually will see various forms of it, so we'll talk about different products. For right now we're just going to talk about the dot product, which is also sometimes referred to as the scalar product, right? So the dot product or the scalar product, those both mean the same thing. So if I give you two vectors, so if I give you vector A, which is going off this way, I give you vector B, and I give you the angle between them, then we define the dot product as, when I take the vector A dot vector B, it is simply the magnitude of A times the magnitude of B times the cosine of the angle between them, right? So that's the mathematical process that we are doing. So again, the dot product is of a vector itself. So what would we have here? So I threw in this note. The dot product of a vector with itself is well defined. What would it be? What if you took vector A times vector A? That's what this is asking. Well, if you took a vector, which is going off some direction, if you did the dot product with itself, right? So if you did the dot product there with itself, then I would have the magnitude of A times the magnitude of A, so obviously that would be A squared, and then cosine of the angle between them. But what is the angle between them? Well, since it's the same vector, the angle between them would be 0, right? So it'd be cosine of 0. So the dot product of a vector with itself would actually just be A squared times cosine of 0, which cosine of 0 is just 1. So it ends up being just A squared. Kind of makes sense, right? We're taking a vector, we're multiplying by itself. Wouldn't we expect that to be A squared? Wouldn't we expect that to be the magnitude times itself? So that kind of makes sense, hopefully. But we'll look at here in the next couple minutes why this is relevant. So why do we actually care about this? Well, if you think about it, this is really what we just did for work, right? Didn't we just say work was force times displacement times cosine of the angle between them? Doesn't that look almost exactly like this equation, right? It's just saying that the work would be the vector of the force times the vector of the displacement times the angle between them. So it'd be the magnitude of the force times the magnitude of the displacement times the angle between, right? So the significance here is the dot product of force times displacement. The dot product of force times displacement is the work done on a system, right? So obviously we can see that if we just kind of look closely at this equation, if we really break this equation down. The reason that's important is we're going to see another way we can find the dot product here, and I'll go ahead and finish that in the final part of this video. So only a few minutes left to get through, but I will finish the other method that we have for finding the dot product in the third and final part of 4-3 notes.